All right, so this is the last one before spring break to finish my inlet end of my screw conveyor. What I decided, I know this week we kind of ran out of time to get back together in this in person. So if you just want to upload what you have done for your first housing solid assignment, that will be fine. I mean, you'll still have to continue on doing what I'm doing, and we can refresh this right after spring break just to make sure we're all up to speed. But that's all I wanted to get this thing to was the flange and the end plate here on the inlet end. So I've got my thing ready here. This one is different than this other end here just because of the nature of the inlet from the discharge. The discharge is incorporated into the end plate here. And so that's how it affects the shape of the end plate to be this rectangular end plate that we're going to bend some flanges on to finish off the profile of this flange. So it's just a different thing going on this end where I've got the inlet coming in on top. And so my end plate shape is really going to be this U shape here, and then it's gonna go up here and have a bend return on it to finish off this kind of three sides of this flange and add the fourth side to it. So if I'll pull up my old conveyor solid here, and this is kind of where we're headed. This is the end plate right here. I'm not going to put these on before, like all I wanted to really get done is to consider my conveyor housing solid done was this end plate, get it on there, and then get this flange to accept that end plate. And of course, this end plate is ready to bend to kind of finish off the fourth side of this flange, like we were going on our discharge end plate as well. So that's really all I wanted to finish was this end plate and this U-shaped flange, and call that my housing, my screw conveyor housing solid at a good completed level and ready to make parts from it at that point. So we've already done this, the extension here and this flange in our last video. And so it's just this one that I've got to figure out maybe this hole pattern and how large it's supposed to be. Although I'm kind of already kind of bound in to matching my overall width to this one. We did that on the end plate of the other end too. Like the dimensions in the chart are just a little bit wider than matching the flange. And I chose to make a little adjustment there and keep my overall width matching my flange width here. So I'm going to do the same when I come over to here. So let's start recreating this from scratch here. This is going to be my, from here to here is going to be my overall width of my end plate. And I'm going to make my end plate first with the holes all in it, and then I'll make the flange that actually goes on the housing to bolt the end plate to. I'll actually project from my end plate that I built, which is just how we built that discharge end plate as well. So trying to follow kind of a similar procedure that I did in the last one. So let's look at this, back to this manual here. And I think it's on the end plates for this. So I can't remember exactly. Oh, maybe it's just right here. It's just right above the feed and discharge spouts is going to be my supporting feet and saddles. I think that's maybe where I find the best. Uh, well, no, not necessarily. Let me look here. This is definitely kind of like a flange scenario that I need to bolt my end plate on. It has that kind of profile. And some of these dimensions are already figured out on my solid model, although B is probably one they're going to tell me some dimension B here, 14 and a half. I think mine's is just a little bit narrower than that, just like it was on the end plate or on the discharge plate. So I'll come back to this a little bit. I think it's maybe further down. I can't remember where some more information on those are. Let me just kind of scroll through. Maybe flush and discharge. We used that one already. And then there's bolts and other dimensions. So it's going to be above here. I was thinking there was just like an end plate page somewhere. Um, Not exactly. Yeah, I think it's above this somewhere, right? There's the housing one again. Some bearings, but there's a bearings through an end plate. Yeah, because I remember we were talking about I'm gonna have to pull the bearing from McMaster car in this little process too. But here's some end plate stuff. They call them type 101s or number 101s, number 103s, whether they're kind of circular or just rectangular or square shaped. But I think there's some more another sheet that has some of the dimensioning right here, maybe. Does it? Yeah. So I think this is the sheet that I might refer to make this end plate right here. A, K, and D. These are like D should already kind of be fit in, or my thing should I'm going to check it, so I'll just see what these dimensions are here. The B and C's, I don't need to totally worry about until I actually have an end plate and need to bend that flange on it. But let's see. So I'll come up here. We've got this style 101 and style 100. Okay. And then ours is 10 inch. Our bearing bore is two, but we went 2 1/8, and I'm going to do the same over on this end. I think, yeah, it's the same size of shaft on the driven as it is the drive. And we made our on our end plate for the discharge, we made it 2 1/8 here for a 2 inch shaft. And then A is saying it should be 14 1/2, but I'm just going to reference that flange I've already made and kind of make it match that width. So it might be just a little bit less than this. I think it was 14 1/4 or something, which is probably about what we are here because I used the same sketch of flange, so it's going to be the same width. And then with the seal, I don't need to worry about these B dimensions yet or C. D is how far it should be, kind of from center of shaft to where that flange bends and comes over to me, should be 6 3/8. And what's E? Maybe some of this doesn't, maybe E, and I don't think I need any of these other variables at this point. Um, but it does it have the hardware that we use in here? Style with bearing. I don't think so, but it does say it's 1/4 inch plate, which is what I used when I made the other end. So I'm going to make these 1/4 inch plate. H is 1/2 inch, but H is to bolt it up to some type of a footing, potentially to hold it up. Just by the nature of how they have these, this is really set to accept some type of a support footing structure. And mine's gonna have a hole patterned up on here to bolt on an even flow bin that sits on top of it that feeds this thing. And on my discharge end, it's going to bolt up to that little funnel squared around. And so I end up kind of changing the way they're finishing off their end plates and incorporating the whole pattern of kind of the flange, the unfinished side of the flange into it. And so I'm going to do the same thing here. And I have that whole pattern in the sketch that I already have pasted to make the flange that's on that we did finished up in last video. So I have some stuff to work with. I'm going to need the bearing that I'm going to use, so I know that it's whole pattern to mount it. And so I think I have what I need. I'm going to pull this up on my other screen to use this A dimension. I'll check this D dimension. K is going to be it's going to be 1/4 inch thickness plate. They don't give you a whole pattern for the holes here. So I'm going to stick with kind of what well, and we didn't really have it great for we didn't get a specific dimensional call out even on a square one. We had to kind of come up with something that was similar hole spacings to what the flanges were calling out. Like I think ours are like is it 1 3 3 3 or some of our hole spacings in our flange. I'm going to try to pattern that. They might tell you how many holes there are. I can't remember if that's one of the things that is called out on spec sheet. Sometimes how many holes around this you would do. But 1 2 3 4 5 6 7 8. That's an 8 hole pattern that it's shown. As long as I'm not spanning too far between these, right? On my other end, I'm in that 4 1/8 inch range between from bolt to bolt. So I'm going to try to keep that in mind. Yeah, because I don't think there's any other even these other images from where they show that they don't give that specific hole pattern like this here. Other than what's been pretty common and a dimension that I've kept pretty consistent is coming in like that 5/8 of an inch, 0.625. I've done that on most of my flanges, and that was based off of some data they gave us from here on the rectangular flanges we built. So I'm kind of keeping that dimension in mind a little bit. I'm going to consider this because this is kind of what I'm bolting into. I knew there was a few other issues. This isn't the end plate necessarily, but this is the flange that's going to that's going to mate with my end plate. And they're going to tell me here that the M is the bolt size, and I think it's going to be a 3/8. M is going to be a 3/8, and 8 of them. This is where I think the number comes up of, it may be in this shape. I would have an 8 hole pattern. Um, that would accept a 3/8 bolt. Um, what you can kind of tell here is it's almost like they've built a pattern here and then they've almost mirrored it over. And so it looks to me like, and this is pretty common with these U-shaped flanges, Some manuals will call them out really specifically. This one doesn't tend to. It kind of leaves you hanging. It does give you the amount they would want and the size of bolt, which is helpful. And then I'm going to use that. I'm going to come in from the edge, at least here, like 5/8 by 5/8 probably to start. And then I'm going to start this pattern. You can kind of tell that this spacing here is probably larger than this spacing here, and that's kind of common in these. Sometimes I like a symmetrical one here too. And so, and if this space was too far, this is right in the bottom of this conveyor, I wouldn't have a problem with adding a bolt here in the middle necessarily. What they're strategically planning on is using that as a foot. And so, which you could still put a hole through there, and then you just have to bolt through the foot, through the flange, through the end plate. So it would maybe take one bolt that's like longer if there was a center hole here. But we'll just see what pattern, and I can reference my old model because I would have determined something then when I did it. But but yeah, it's kind of a little unclear. And this was clearly given, but I chose to kind of make it just a little bit more symmetrical. Well, I made mine totally symmetrical, but and I'm gonna try to do the same thing with the whole pattern for this other end plate. But what I'm gonna do is get started here. So I'm gonna start with a sketch on this face. My end plate would bolt right to this. So. By the way, if you've never toggled this down, we talked about piping ISOs and drawings today. You can start a 3D sketch, which can be used to make piping isometrics. So we haven't drawn any 3D sketches, but I do use that when I do some structural steel in here, and I'm hoping to do that before the end of the semester to get the deck on the side of this conveyor built. Would be my next I'd like to get the conveyor built and ready to go, and maybe the mounts to the floor to hold it up in the air, but then a deck to stand on. And we would explore 3D sketching when we get to that point. So, and I think it's really valuable to dabble in and get a little familiar with because you can sketch parts out in 3D. In fact, the 2D sketches that I'm doing, I could do a 3D sketch. Um, but they're kind of complicated, just like 3D is. But okay, so I'm just going to start a 2D sketch right here on this end plate, and I'm going to do some projections here. Similar to how I did my discharge end plate. I kind of want to know how overall wide it is. That's these right here. I want to know where the top of this is because mine's gonna be an end plate that's gonna have a bend incorporated into it. So I'm gonna offset the thickness of my end plate material that's gonna be bent, which is 1/4 inch material. So I think on our other end we offset this line 1/4 inch, 0.25. That's where my end plate technically starts, that low, and then it bends right here. And then it's going to be this wide from that point over to that point, and then it's going to be this shape right here. And so, um, what's the best way to do that? I don't know. I could almost start like I don't know. I could kind of sketch this and almost draw this a little bit manually. I'm going to just make these constructions, but and then I'm going to come in here with a line. And I'm going to say if I can project over from there and where that meets right here, I'm looking for where that point is. That's the point that lines up with this top of my plate and that overall width right there. And then this thing would come down to this center point, right? Oh, this is like we've drawn other things. I want to make sure it's perpendicular to what I'm drawing like that, and then it's going to line up with that center point. And then from there to there, I can click, and then if I do that left click and hold, I can make this shape over here and kind of target that point. I may have to zoom in a little bit here, and I can adjust this after if I don't get it right either. But I'm kind of looking like there's my target showing up. So I'm going to unclick there, and then I'm going to connect this back up to here. Yeah, yeah. I'm going to tie this back in over here. Okay. And so you wanted to know this distance here? Oh, like, so if I measure from here over, I think it's 14 1/4, if that sounds right, maybe. 14 1/4 is how far those are. Yep. Yeah, so if you didn't have those, yeah, once you draw those in, you'll have those as a reference. But yeah, 14 1/4. And the only thing that's constrained on here is this, because I locked it into that line that I had offset. So th this thing needs to be like here's how it would flex, right? I can kind of adjust how it flexes, and I can say, oh, I can correct some of that just by doing like a vertical constraint from the end of the constrained line here to the end that I have projected. Or if you had a dimension, if you have to put 14 and a quarter in there, that will constrain it. And then I also need to do a constraint over here. This line is this line. And then the only thing that's missing here now is that you can see that this is what still is allowed to flex is what the diameter of this is. And it's got a center point that's unconstrained. And all I need to do is constrain that to my existing center of screw, or kind of my center of my whole process that I've been developing here. Is that's the screw center through here. So I'm just going to constrain those, coincident constraint that to this, if you sketched it that way. And really, it's just mostly geometrically constrained, right? Uh, yeah. I mean, that's just a coincident constraint because the center doesn't know where the center is, and so I constrained it to the origin center point, which my sketch plane has it automatically as a selectable geometry. If it doesn't, it's the center point. You could project the center point here, project geometry, center point. That's what it is. But I think you should mine. I haven't had to project that. It's been available in my yours made yours really long. Like mine's like this. Hmm. I've never, mine before I even started, I kept that center point in my original model as I knew that was going to be it was a thought that I had way ahead of the game that I was like, that is going to be the center pipe. And so I would say if your sketching isn't like lined up where mine is over center point, then you could what you could do is you could okay, cool. Because if you didn't, you could project this geometry and it would have that center along with it. So it wouldn't be the end of the world if you weren't working from the origin center point, but then you would have to just reference some geometry that did have a center point. And so, yeah. And that happens to us because sometimes our stuff falls off the center point, and I have to establish some other projected geometry. But this is that. And then this end plate is really solid. I'm just going to put in the hole pattern now for it. It's going to be an end plate that I extrude that's a 1/4 inch thick. Only I'm just going to build that little 8 hole pattern around here. And so I'm going to do it with points as well. Like I'll just place a random point out here that's got no constraints on it. And what we did on the other end, I'm going to do here, which was just kind of pulling some data from those other flange details, which is this is 0.625 on our other flanges coming in from the edge, 0.625. That's what we've done here. That's what we've done all over down there, which is kind of nice because it just gets you away, like to put in the hardware, the closer you would drive this hole to the skin and this, the harder it is going to be. And if you get too close, you won't even be able to fit the bolt head up against too close. So by having, I mean, it doesn't look like it's centered in the flange for sure. Like when you look at that, it's not centered. It's kind of favoring the outside edge. And that's because you're kind of getting, like, in some ways it's an advantage because you're getting hardware that's easier to install. So it's not so cramped up into a wall of something. But I probably could center it honestly here too and still have the room to install the hardware. But it's pretty common in flanges that we pull those to the outside edge. Uh, and it's mostly to create space for people that have to take these on and off. And they make that easier to do. So I like this 0.625 dimension. I still feel like I mean, there's going to be a threshold how far over you could go because you don't want to minimize how strong this joint is and get this hole too close to like an outside edge and have it potentially tear out. It would take a massive amount of force to tear something out, but it will if you get it too close to an edge. And then there's some forces that happen unexpectedly. So I'm saying 5/8 seems like a nice amount of meat still there from edge to hole. So that's why I've kind of used that dimension over and over. Is it seems like it's a good dimension. And then when we initially started ours, we came away that far too, the same dimension here. So I'm just using the 625 as a place to start. And then and then it's going to just really be like a full, like a symmetrical pattern. Like it wants me to do like 4 holes over here and then 4 holes over there. And then I'll check really quick on, I probably did something slightly different on mine. I don't know, but here's how mine kind of ended up is well, I've got one, two, three, four, five, six, seven, eight, nine, 10. And it's probably, I actually probably increased my number because I didn't like how far apart the holes were getting. And just because the flange details that I have in that document kind of call out those, like some of the dimensions on that rectangular flange were four. What I'm referencing is this. Actually, I'm right on the sheet actually. Some of these spacings were different, L's, M's, and N's, but none of them were ever any longer than 4 3/8 of an inch. So I think what I determined is when I looked at and they didn't give me the specific data to use. I was just like, well, I don't want to go beyond this. So, I mean, this to me is a good baseline of how far apart I should put my hardware. And so I'm making a little bit of a designer judgment call here because I feel like I have some leeway. And I like the 5/8 dimension coming in, but I just want to kind of figure out, oh, can I keep these kind of an equal space all the way around? And I've probably done that. I've probably done an equal space. These are kind of hard to measure, but I can kind of go here to here. If I was just to measure it straight, and I can't say they're all the same, but I was kind of checking. 40463. Yeah. And that's a little bit shorter. And then over to here. Oh yeah. So it's kind of an oddball size, but so I can't say I'm going to totally recreate this. I could find out what my sketch was on this if I just kind of figure out where my inlet right here is that extrusion. Here's the whole pattern, probably from that same sketch. So let me open this old sketch up here. Sorry, here's my edit sketch. I think I actually had drawn it somewhere else and then projected over to this because these are projected holes that I've got here. So it's probably in a hole pattern. Maybe I built mine backwards, but I built not backwards, just a different way that must have put the flange holes in. Um, yeah. Oh, this is maybe it right here. Yeah, I think I originally drew the flange. I'm drawing it a little bit reverse of how I did this the first time. I'm drawing the end plate first, and I was going to draw the flange next. Looks like for whatever reason when I was designing last time that I built the flange first and then projected those sketches over to my end plate. It's like tomato tomato. It doesn't really matter. I'm going to get into this sketch though and just take a look at it. This is what I ended up using, which is totally different than what I've done. Uh, currently, but what I'm kind of looking for is this same kind of a similar pattern. It looks like I'm going to use like a five, um, instead of being four, I'm going to be like a five hole pattern. And so you can kind of see I've broke up my pattern into being kind of like what the linear measurements are here. And then I kind of created a new pattern. Looks like I've got one that needs constraint. I've got like a constraint missing here. That'll mess everything up. So I'd have to get back in here and constrain that. But um, yeah, and then I've done like a 36-degree pattern is what I've kind of determined maybe was going to give me like a nice measurement between point to point and not feel like I was like getting way beyond 4 3/8 of an inch or way too short of four. I don't want it to be 2 inches apart either. I'm looking to kind of be in the range of 4 to 4 3/8, like that rectangular flange gave me some 4 to 4 3/8 kind of ranges of measurements. So and it looks like I did similar here. So my first point that I've actually placed it in the same place that I started in the original sketch, 5/8 by 5/8. And so I think that's still a good place to start. It looks like I've used this particular dimension, but I think what I did was I'll show you how I think I understand what I've done here. And this is sometimes how you're informed by somebody else's design. Like when you're working in an existing system and you might not be starting from scratch, you could be working with somebody else's model, and it would just be a matter of jumping into their sketches, trying to make sense out of them. Sometimes I'm trying to recreate what they've done. If it worked well, and it's a design that we've vetted that works, then you can like you spend a lot of to me in the industry when you spend a lot of time in other people's models and it's kind of like getting into their brain and you find stuff that you don't like that people do and you also find little tricks and hacks where you're like, ooh, I kind of like how they did that. So use that to your advantage. um my thought process is, there are times that you're slow as a drafter and you're waiting for the next job. And instead of just sitting there like spinning your thumbs or continually bugging your boss if I need some work, what do you got to give me to work? I feel like there's always like um, time to spend in someone else's model. There's like I can do my own homework at times. I can refine my own models. And so to me, I always make my own like laundry list of busy work to so that when I'm bored and waiting for somebody to send me a job, because your bosses know that. They know that you need work. And sometimes you're just waiting for sales and customers to decide specifics. And so you're just kind of waiting, the work's coming. You should be able to find things to fill that time and to help you as a drafter designer. And getting into other people's models is part of that process to me. So this is helpful to me. Maybe I hadn't built one of these before, and I was like, well, somebody else has. Let me go into this model and see what they're doing. They're not necessarily keeping the exact like spacing, but they're building kind of a symmetrical pattern here. And you can tell from the documentation that when we get into these kind of flanges, they are kind of complicated, and it's almost like they don't even define it for me because they're just like, hey, just make something that'll work. We think it needs at least an 8-hole pattern, and obviously there's some differences in maybe the hole to hole center spacing here. So I feel like I've got some leeway as long as I come up with something that'll work. I especially have control over that if I am building the stuff that's bolting onto these, and there's never another customer that's going to bolt onto mine. If I have that situation going on to where like I have to be worried about what something that someone else builds that bolts to mine, well then we have to have a discussion in places like this to make sure I don't deliver a hole pattern that they're not anticipating. And sometimes that happens as an internal, like from drafter to drafter. You're building that, I'm building this. Hey, whatever our flanges, we got to match. Um, and as long as things both up and match, there's generally not an issue. Whether I put in 8 or I put in 10. So, long story short, I feel like I kind of understood what my thought process was here. So I'm going to kind of recreate that here, only I'm on the end plate. I've got a start of this. And so what I could tell was I end up kind of terminating a point right here at where this goes from a straight to starting to go around the housing here. I put a bolt there and I put a bolt there. And then I put a bolt and maybe I had like one, two, three, four. How many did I have? One. Let me see at this. It was a 10-hole pattern, right? It was like one, two, three, four, five, six, seven, eight, nine, 10. Yeah, yeah. So what I end up having is a hole here, here, and then one here, here, and one here, here. And these were all kind of equal like degrees around this on the circular side of things. And then from here up, I just put in another bolt here and then the one at the top. So and I feel like maybe I can do this as a mirrored, like I'm going to build the pattern and then I'm going to like just mirror it across the center. So I feel like if I just build it from center over this way, so what I'm going to do is I'm going to project my planes here. That's one projection I'm going to do. And then that might be, I might need this other projection here this well. So I'm just projecting my two planes, two of my main origin planes. Uh, as kind of just some construction material. I'm going to place another point. What I said is I think I ended up placing a point here, which is going to be 5/8 in. So I will end up like constraining it to that right there. I'm just going to build out this half, I think. So this point, I'm bound on that line that I just projected, so I can't go up and down from there. I'm constrained that way. I just need to do like a vertical constraint to say here to here is going to be constrained. At this point, it starts and I could build out a bolt circle construction line. I'm probably going to need to. Um, but what am I going to do here? I'm going to say, um, yeah, I probably will end up having to put that out. Like I need a circle radius. This is kind of a construction circle. Construction circle from center here. I'm going to pull it out to here. And I can just leave that like that for a minute. But this ends up being kind of like a bolt circle pattern where those holes are going to live. And that's just driven by this dimension lined up with it and then pulled a snapped a circle out there. And now I've got a bolt circle for this little section that I need to apply. Essentially what I need is a point. And so I'm gonna apply some points to that circle now because I just want them to be constrained to that at least. There's going to be like one here somewhere and one here. And is that many? One, two, three, four, five. Yeah, I think that's it. I think that's the only ones I need. Or is like that, like this. And then what I thought I did is I kind of looked at this as a semicircle pattern, and I just decided I want them to be equally spaced. So what I did is some more construction lines, kind of like hooking this to this point. And then from here again, I'm drawing these as kind of construction points that I can add an angular measurement to. So they're constrained from center to this unconstrained point. So if I move this, maybe, or if I move this point, that line should stay with it if I'm flexing it like this. There's that line that I drew and those points are constrained together. So that just allows me a place to like put in an angular measurement here. And what I have is if I just analyze this as a circle, right? It's just like um, I would have like I want the spacing to be the same between here to here, here to here, and then here to the next one, which is over on the other side. So I kind of have to consider that whatever the degree of measurement between that and that is, it's kind of half of that from here to here, if that makes sense, I think. But it's going to end up with a pattern like this. And the only other one I'm missing is another point that's going to be on this in alignment with this and in here somewhere, right? I want it constrained up and down to that, but I don't know how far down it goes. So that's one, two, three, four, five holes. I'll be able to mirror those across, and mine will end up with a 10-hole pattern. And hopefully they're not much more than 4 3/8 apart. And so this is the question I could look at this is this going to be bigger than this? Let me look at this other sketch here. I don't think so. It looks like I used 36 degrees, but then it's 36 degrees over center. So this is half of 36 right there. And I would have come up with that just by saying, okay, um, I can come up with how many, like this is 180 degrees essentially from here to here. And if I've got in 180 degrees, I'm going to have like one, two, three, four, five spacing. So how I came up with that degree was I did that math. I said I'm in 180 degrees little circle here. I'm going to divide that by five spaces, and they each end up being 36 degrees apart. And that's just keeping like the same amount of degrees of space between that, between this, and then between where it jumps over center and goes to the next one and to the next one, next one. So it's like a symmetrical kind of pattern, kind of this array pattern. And so that's what I'm going to apply is these dimensions. I'm going to say that's 180 divided by five spaces. This ends up needing to be 36 degrees. 36. And is that what I did again? It's going to be that. I'm just going to use that as my reference dimension. It doesn't quite look right to me necessarily. Maybe I'm right. What is it? This should be 18 degrees, I guess. Yeah, it's 18. I think that's right. That's what I did. I think that's what I mirrored over to the other side. Just kind of looks funny, but those are all constrained now too. That's all constrained geometry. I just have that one dimension. Maybe I'll pull these off my part a little bit, but 36. And now I just need to know what the distance is between here and here, and I want to be half of that, right? So I have constrained geometry. I can just measure this. I can say, oh, this is this point to this point. I just want to place another bolt halfway in between there. This is 7 3/4. So sometimes when I'm like when I take a measurement, sometimes I'll copy and paste that dimension. Like here it is, it's in a box, right? Your little measurement. Sometimes these float around. It looks like I docked mine at one time, but I can pull it back off again. But these are selectable here. I mean, sometimes I just grab the digits, but you control copy. I can say done here, and then I can dimension this. And I can insert that. I just copy paste, control V. It would be that, but it'd be like divided by 2. I mean, that's a quick kind of hack way to get that dimension. It's 3.875 if I would have sat and did the math. But sometimes when you pull a measurement that's really odd, you can just copy and paste it into maybe where you need to use that measurement. So, that's handy to remember. And then I think I need to vertically constrain this. Even though I used it, I kind of referenced it when I placed it. I never actually totally constrained it. So that is that. And then this means that this should, if I did my math right, this should be from here to here. It was not going to want to apply this dimension because it's redundant. But if you accept it as a driven dimension, it's the same as this here. So what we've built is kind of a symmetrical pattern of a bolt hole pattern. Um, and I can mirror that over now. So now I feel like within the same sketch, just take this geometry. I'm going to say mirror it. It needs me to select yeah, go ahead. This one here, this one, this one. Yeah, let's see here. That one is and really it's just determined because I'm coming in from here to over to this point as 0.625. So it's let me see. Its measurement is 13-inch diameter is what the bolt circle would be. 13-inch from outside to inside. Because this is an 11-inch housing, right? That's an 11-inch diameter. That's critical. This is 11-inch. This one was driven, the width of mine, which is 14 and a quarter, was really because I'm holding to be parallel here, so that these are in the same. So I don't have one that's a little bit longer than the other. And so that 14 and a quarter width, yeah. Actually, yeah, I only have like 4 dimensions that I've really entered in this sketch, just the quarter-inch offset. You found some errors there, right here. So you may not have this either. Do you have this little rise done? Because we did that. Oh yeah. And I pulled that from the data. I think it's like two and a quarter and that's from the chart. That's from the book itself. There are some things that following a conveyor standard help us, and one of them is that we don't make this too short to where I can actually get in here and fabricate it. It's a pretty small area. And of course, if you have to put that flange on there, you're upside down to do it this way. So a lot of people would put that flange on by turning this over with a crane and getting in here to do the welding that might be necessary. But yeah, we did talk about that. Yeah, that's probably it. You just missed that I have a little inlet height that I've added there, two and a quarter. This one is actually 3/16, so it's 0.1875. So any of my flanges that I'm going to weld to the housing are going to be 3/16 of an inch from our chart, kind of. Yeah, 1.1875. And that's the same thickness I kept this one and the same thickness that I made this one that welds to it. And when I build the flange on this end, this one is 3/16 of an inch. And it will be the one that goes on the housing too. However, the end plate will be quarter of an inch. And those are just two differences that show up in the SEMA standard. Like there could be somebody could argue, a designer could be like, I'm just going to make them all the same material. And I'm like, well, then you kind of, to me, got to make them all quarter-inch material because the end plates definitely need to be quarter-inch material. So that means my stiffeners and my other flanges are going to be kind of oversized, which wouldn't be the end of the world. So, I think I told you, like in a small manufacturing facility, I might say, I'll make them all the same material. In a large manufacturing place, we're always cutting. I mean, when they're going to be laser cutting parts, they're going to be continuously like nesting a lot of projects. And so having a few different materials is not is pretty normal, I would say. Like this doesn't stand out to me as to be a normal. But I can see that some designers might just say, "Well, make them symmetrical," because we do as designers, we think make things symmetrical and kind of like as much as I can unless there's a good reason not to. So I think of symmetry and it helps for part failure. Like if you're making things left and right handed, they can be assembled incorrectly. There are times when you have to do that for sure. But anytime I have control to make things symmetrical, I try to. And that goes that way with selecting materials. I avoid oddball materials. and I avoid trying to make things out of 15 different materials versus just a couple or a handful of few different materials. So right now the materials we're thinking about on the housing are 12 gauge sheet metal for the skin, some 3/16 on the flanges that I weld to the housing, and then some bolt-on quarter-inch plates. So I'm really only working with three different types of material here. Anyway, you just put me off on a tangent, but that's that thought. No, that's good. No, I like these. These make me think of why, right? And I like that. Because there is a thought process behind everything in some ways. What I have to do is just finish my mirror pattern here. Mirror, mirror this one, that little piece of geometry. I'm just mirroring the points and they should stay symmetrical. I already have that plane line projected, so I already have a mirror line. I like in CAD where you can pick 2 points as the line. Like it's a little more painful in Inventor. It likes you to have a line. So sometimes I have to draw these construction lines. I already had, not that I would planned for that, but I already projected my planes here. So I already have a mirror line. But there are some things about CAD that I do prefer over Inventor actually. And establishing a mirror line with 2 points I like. But so I'm gonna call Autodesk after this, and they're gonna fix that for me. I know. No, they're not. But they do take input like that. I think that I accidentally selected that as geometry, so I've got to shift select that I don't want to mirror that. I don't think. Let me make sure I hadn't. I'm going to reselect my mirror. Sorry. That one. Just pick my geometry that I'm mirroring first. Then I'll pick my mirror line. Maybe I did do that correct. Yeah, I probably did. Probably had it correct. Apply that thing. It applies all those symmetrical constraints automatically for us, which are painful to undo. They really are. Like using mirror and then trying to like fix that later. It's hard. Because they're kind of all individual in some ways. But anyway, it works for me here. If you get it right the first time, it helps. If you gotta modify these kind of sketches, they're a little bit of work. And then if you delete them and they're driving a hole, well, then that messes that up later, right? So you have to think of when you've used projected geometry or you've used your geometry and then you decide to delete it and you had features from it. Oh, it's just kind of it's just kind of a rat's nest you have to untangle. But it's the holes on this angle, like these here. Oh yeah, it would be well because you have a dimension applied. Oh yeah, and then I have mine snapped to this. I have mine snapped to that. So the way I started my pattern was I placed this one first, and uh, and I constrained it to be in line with that one, so they were over the top of each other. Yeah, I don't know. You just gotta chase it. Yeah. Oh yeah, I got you. Yeah. That's it. So that is kind of done. Only this is the end plate, so it has a hole in it in the middle and it has a bearing hole pattern. So I've still got some more sketching to do here to further complicate this. At some point, sometimes if your sketches get too complicated, it's better to make probably a second sketch. I don't think I'm there yet. This is still a pretty simple sketch, only a few pieces of data. But you can make that judgment call. There are times when I'm like, okay, that's enough in one sketch to have to come in and work on. This one, I still think I can keep going. So. It's a 2-inch shaft coming through this way as well. So I'm going to put a circle in here, not construction though this time. I want this just to be the circle that's going to be in the end plate and it's going to be on this center point. And it's 2 1/8. That's the same size that I put in the discharge end plate right there, 2 1/8. I kind of still had that memorized because it isn't in our SEMA standard, but I do know that I need clearance for the shaft to come through and then go into my bearing. And now what I need is the bearing mount hole pattern. I don't have it. We pulled the bearing on the other end, but it's a different bearing. The bearing on this end, I called it the drive bearing, and it's a thrust capable bearing. And so it's special in some way. It's more expensive for sure. On the other end, on a driven end of a system, and I call this the drive end because that's where the gearbox and motor are going to be. And the bearing is going to be a thrust bearing, which just is it's just how it's built and designed is made to allow the thrust. What thrust means is as I'm pushing product this way through my conveyor, the forces are actually pushing my auger the other way. So I have thrust loading on your bearings the opposite way the product is moving through your thing. It's kind of like a teeter-totter situation here. When forces are driving something some way, there's another force going the other way. And so these bearings can actually take that kind of thrust. And thrust bearings can take kind of like radial load and they can take linear load. So, and some thrust bearings are designed for more load in one forces in one way than the other. But that's an engineering call more than a drafting call. But it's good to be aware of bearings matter. Thrust bearings are specific to take thrust. On the other end here, I don't really have any thrust, so I just have I actually buy a cheaper bearing, essentially is what I'm trying to do, save some money. And I just buy a driven bearing. It's just a roller bearing. And so what I have in our documentation here is a link to that bearing. So we pulled the drive thrust bearing from McMaster Car. I'm gonna pull the driven bearing from McMaster Car. And so if you have this document up, you can control and follow that link. If not, I'll give you the control. It's yeah, it's in my design specification from engineering sheet, and we're gonna pull the driven bearing now right here. You what? I don't have the driven downloader yet either. So that's what I'm doing. Yeah, maybe. And so when I clicked on my link, it's this one. I have the drive one, and then I've got to do the same concept here. So it's like if you go to McMaster Car, or if you follow that link, it's yeah 5967K93 is the McMaster Car part number. And you can either enter that in. It looks like it'll go right to this, or if you follow my link, it'll be to this bearing, which is a cheaper bearing. I don't know I don't remember seeing what the cost of the other one is. This is a $143 bearing. Stand by for a second. We'll check the difference in prices since I was just kind of mentioning that. This should be substantially more expensive of bearing. Yeah, it's $564. So there's a reason why I would choose not. I mean, I only need one thrust bearing on this, and so I save a lot of money by not putting two of these kind of bearings on there. These are expensive bearings. Um, Taper rolled bearings with full bolt flange. Yeah, they're expensive. So that's the one we drove. That's the one we pulled out the other day, and this is the one I need today. Is a yeah 5967K93, way cheaper bearing, $143. I just want to pull the data sheets into my data folder, so I'll do that first. Here's the product sheet. This will help me to do my design work. So I'm going to download that, save it. Mine are in my folder somewhere, right? In my CAD folder for 1138. Oh, there would have been no way I could have finished all this in this. I was ridiculous to even think I could have. Screw Conveyor for this year, and I have a resources folder this time around. And I've kept these just whatever the downloadable description is, so they're kind of big descriptions, but it for sure has the MasterCard. As you get used to this, and if you know your resources that you used a lot, not that everybody uses MasterCard, some people use more manufacturing websites, but you start to understand. Yeah, I mean, anyway, I don't know. If you pull this up, and usually they'll have a title block where it says where they came from. So I don't have that in there, but just by opening the document, I could figure out what is it, who supplied this. I'm going to tell you, like, I had the string. Sorry, this will be in my video, but I had the strangest experience that, what I'll do is I'll go take a walk around here sometimes and think. And I was coming back in yesterday and I didn't say anything out loud. I just was thinking to myself, I got to pull some sensors into this eventually towards the end, like some safety sensors is what I'm thinking of, or some level sensors for the even flow bin. You can a sensor might be a laser beam that shoots across and that the auger won't run unless there's product that hits that laser beam kind of like it, and if the product drops below that laser beam sensor, the auger might stop and wait for product to build up again. So that's like an instrumentation that's going on here, is that you've got this little even flow hopper full of potatoes, and once it gets, you could put a level sensor in the lower part that says I want the auger to turn off once it gets this low, and I don't have any, so it just doesn't keep running this auger if it doesn't need it. And so we could put a level sensor in there, but all I was doing was having a thought in my mind as I was walking down the hall. Oh yeah, I gotta decide what sensors to use. Well, then I was watching YouTube last night, and I had an ad that was Endress Hauser, which is the type of sensors I use when at Idaho Steel Products. They're a really nice European-made sensor, I think. They might make some here in the States, but Enders Hauser, like a really nice, expensive sensor. And I have not seen an Enders. I couldn't even tell. I hadn't thought of the. I think the world is spooky, is all I'm saying. Because I got fed an ad for an Enders Hauser sensor. I hadn't typed and searched for sensors since I hadn't even thought of Enders Hauser being the manufacturer since I left Idaho Steel. But when I saw that come up, I'm like, that's the sensors I need. Holy shit. Anyway, it was weird to me. It was a weird, like, Twilight Zone moment. Anyway, yeah, that's eventually we'll put a sensor on here. And so your devices are listening to you, even your mind, if you don't even verbalize what you're, they already know what you're thinking. Strange. Okay. Thanks, CIA. Thanks, FBI. So I just need to pull the I'm sure this happens to you guys at times too. It's just like spooky. So weird. Who is listening? Big Brother is listening. I need the 3D step file for this though too. So while I'm in here, I'm gonna pull this. I got my data sheet saved to my resources. I'm gonna pull this thing, download it. I should have picked a folder to download it, but I just put it in my download. So I'm just gonna go boot it over to my parts folder. So I'll just jump over to my folders here, downloads. There it is. I'll expand my menu. Where I wanted it to go is in my Screw Conveyor 2026 parts. I've just been dropping these step files in my parts folder as well. So now I've got one that I can open. So I'll go ahead and open that. I have the information on the spreadsheet or the spec sheet, or I can just go ahead and open the bearing. And I'm going to save it as a new name anyway. This will be my third part in my assembly, really. So I'll finish this sketch for a minute. I'm going to come back to it. I'm not going to do any extrusions yet. I want to finish the whole pattern for the bearing. So let's just open up that thing where I saved it. So I'm going to go to open. I've got my project loaded, right? So it's just going to go right to my parts folder is actually the last thing I was looking in here. And that's where the step file is, only it's only looking for inventor files. So make sure you toggle these on to all files or whatever kind of file you're looking for. There's my step files. It's the set screw shaft mounted ball bearing right here, the 5961. So I'm going to open this one, let it convert it to an inventor file. Okay. And there it is. I just need to do is save as. So there's the next bearing that's going to go in my model at the assembly level. It's got a grease zerk spot for it. It's got the set screws. Even this is great. I can do a quick double check here. It should be like 5 1/8 is what I was noticing on that sheet. 5.26 actually, just a little bit over an eighth from hole to hole. I think it's a symmetrical pattern though. They're smart too. This should be a symmetrical hole pattern. It's easier. And then what's the size of this? I didn't see the diameter though. So it's pretty big. 687, and it would really accept 1/2 inch hardware. Heck, that's even bigger than 5/8 hardware. So I have to make a decision on what kind of threads to use here to hold it up, but at least I know the whole pattern, so I can just at least start with that. And I'm going to do a quick save as here. File, save as. I want this thing to rename it. I want the description to carry the McMaster car information, but I don't want my part name to be that. So I'm going to say, hey, it's SC2. I'll just change this to 3. This is my actually only my third part in my design process that I've created. And I'll say save. And then I think on that last bearing, I think we determined that I just needed to change the description. Um, yeah, and I'll see those descriptions show up on my parts list, so I can refine them later if I kind of name one funky and forget what the name of the other one is. But it's in the iProperties for the part, and on the project tab is our description. This is not a helpful step. AP203 is not a helpful description, which is what just populates on my parts list the way our templates are set up. So I really want this one to show up. I think what we wrote is I'm gonna copy just the MasterCard part number here. Let's see, copy that. And I think I ended up putting that in here maybe first. Then I said McMastercar. Um, Something like this. If my description doesn't match what my other bearing is, I can come back to this description and kind of make it match a little better. But just that it's extra car driven bearing, I'll come back in and decide. And I've got the number for sure. So and the manufacturer. So I probably could just delete the rest and just make sure I have the part number and the manufacturer because purchasing technically is to me who reads my parts list and orders parts, unless I am the drafter, designer, and purchaser, which does happen in some companies that are small. Um, so this is good. This will be what I want to, the whole pattern that I want for here. So I'm back into this sketch now, and let's do that. Edit this sketch. And I think I just used a square when I did this last, right? I brought in a square that I used the points for my hole creation. And so I just need this to be 5.126 by 5.126, like a square hole pattern. And then I just need to constrain it so that's it's for me aligned with my center. And so I just did some vertical constraints here from midpoint here to center point. That'll push it over that way. And then I did the opposite vertical or horizontal constraint here from midpoint of that to there. And then I've got a constrained. And then I should have done this before, but I'll hold down control and select all these lines. I just want this to be construction too. That is the whole pattern on the corners. So at this point, I feel like I'm really ready to make my end plates. So I'm going to say finish and let's extrude that thing and then put some holes in it. So I'll say extrude it first, this profile without the center hole, of course. And maybe I'll make it a new solid. There's no reason why I shouldn't make this maybe a new solid. Um, it's an end plate. Maybe I should have been making more new solids as I went along, but it's okay. I'll work with that, what I didn't do later. I don't, or something to refine later, right? When I'm down, when my downtime is there, I can refine some base models, but I'll make that a new solid. I only want it to be 0.25 of an inch thick. It's quarter-inch plate. That's my end plate. I'll say okay. I'll have to turn back on my sketch now. Quarter of an inch thick. Yep, quarter inch. That matches this end plate's quarter-inch thick. So I have these two parts that are quarter-inch now. 0.25. And I just need that sketch to use it for a bunch more stuff here. So I'm going to turn this on and use it. I need to create those holes through it. So the holes are going to be a clearance hole for 3/8 hardware. So we've been doing a lot of that. It's the same. I don't know if it's the last one I use and it'll be loaded, but it's just going to be a hole on these points through the end plate it's picking up 10 positions. Yep, those are my 10 positions through that solid. Let me escape that solid. Just make sure it's selecting the right solid. It's only this solid that I want to push that through. So it was already picking up my 10 points. I just needed X out your solids and X out your points. Like you could start from scratch with nothing and select the ones that you would want. So here's me. I feel like once you start selecting geometry for these holes, sometimes it'll just infer which solid they belong to, but then you got to come back here and say not that solid. I think it's the one that's turning yellow actually. I'm going to say not that. I want, and then now I'm on solid selection, and now I'm going to say this solid because it is an individual solid. Yep, I extruded out, just kind of like it would live and how it's really going to live because that housing solid represents the volume inside. I turn back on my sketch. Yeah, it's going to consume that with an extrusion, and then you just got to turn it back on. So I'm using this for multiple features, this one sketch. And I do that a lot. It causes a domino effect of problems sometimes when you do that, but if it doesn't have a problem, it's great because it will automatically do things for you. And then I want it as a clearance hole. And mine is loading exactly what I want, but if yours doesn't, it's got to be this ANSI screw threads with a hex head bolt is what I'm going to bolt these together with. It's going to be 3/8, and I just want a normal clearance fit, so it's got a little bit of space tolerance built into it. And then I'm going to select the surface for it to terminate. Really, I don't have to because it's just through this solid. So you could say through all here, and it kind of means the same. When I have to watch whether it's through all or to a surface is sometimes when it's going through multiple solids, and I'm not anticipating that it should. So here, this is it for me. These are my holes. Oh, and mine says it can't even do that anyway, and I don't know why. It could be my solid selection for I don't know, like I'm going to edit this now and see maybe if I say to next and select, this is going from here to here to that surface. Maybe that's it. It just didn't like me maybe I needed to switch my direction or something, but this is going to work for me, I think. I see the creation happen here. So I feel like that, I don't know. Yeah, it didn't like me to go through all there. It could have just been, I probably could have troubleshot a little bit more, but that'll work for me. I'm just trying to go through that surface. And then if I change the thickness of that surface, having instead of you see me a lot when I make holes, I generally don't input the number of the hole. I'm generally selecting surfaces or through solids. It's because then when I change the thicknesses of those things, if I have to, then I don't have to even worry about that feature not working. But if you enter dimensions, you always have to go back in and re-enter the new dimension of the extrusion. And so that's not a bad thing either. It's just you would learn over time to be like, is there a way to just avoid more data entry? And one of them is, select surfaces to terminate stuff or select through solids. You've seen me do that a lot all this semester, so I continue to do it. And this is kind of a Dunzo plate. No, 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 it's not. I've got the holes. This is where I turned mine to view it as a wire frame because I could see I need holes to mount the bearings to that end plate. So, I mean, that's the other thing my end plate is doing is supporting my bearing. It's what my bearing bolts to, which is one reason why it's probably quarter inch material. It's a little bit thicker, a little bit heavier duty. It's doing more things for us here. It's also holding the housing form shape, and so it's just structurally more sound slightly. These holes, the middle hole is just one that I didn't really cut at all. It's just I never selected it as geometry because so when I did the extrusion, I didn't let it select. No, there should be a hole all the way through. There should be no material in that. That's where the auger comes through the end plate, the shaft to go. Yeah. So that should be a through hole. That's 2 1/8 inch in diameter. Yeah. And then what I've got to decide here. So what I've got going on is a little bit weird. My bearings are kind of different. I mean, they are two different bearings. That's a normal. They even have different like kind of hole patterns to mount them. That's pretty normal on from bearing to bearing. They'll still both support a 2 inch shaft. One will support thrust. One isn't designed to. It's just a driven bearing. And so there are some features that are different. What else is different is the kind of the size of hardware to mount it. And so I'm just going to pull up the data sheet again and just take a quick read through it. I don't have that memorized by any means. I have it saved in my folder here for my screw conveyor resources here. I have this is the new data sheet that I pulled down. So I'm just going to do a quick peruse through here. It does show me that it's 0.687 hole size for a bolt. It's for shaft diameter 2. It can handle 2 degrees of misalignment because these are on it. This is like a bearing, and what you don't see in here is they're little roller. But I mean, the way they make bearings is pretty amazing. It's a super awesome precision engineering process for sure. But they're just these little roller, not necessarily just roller balls. Sometimes they're little cylinders that are and so sometimes they're roller ball bearings, yes, ball bearings, but other times what's kind of hidden and sealed in this housing is sometimes just little cylindrical round parts that roll around each other. And they're a little more stable. Like roller bearings, ball bearings, I should say, can take a little bit more maybe misalignment capability. Like this is saying 2 degrees of misalignment. Makes me think there's probably more of a cylindrical shaped roller in this little housing. That it won't take that much. You can't be that far out of alignment to drive this bearing. Whereas ball bearings are just these little spheres all around in a housing, and they can take pretty heavy misalignment because you're kind of riding on a spherical shaped components where sometimes sometimes in these bearings you're riding on cylindrical shaped bearings that kind of help hold things in alignment better and you have to be closer aligned. And then in our thrust bearing they're like tapered rollers, so the rollers are in kind of this little cage system, and then they're really fancy actually. So they're kind of like a tape. When it says tapered roller, it's kind of like the little rolling components are actually tapered and in a little rack, and which allows them to hold some thrust as well. So they're just designed with the engineering they need in mind, and they're amazing. So amazing, amazing. Take them for granted for sure because they don't. I can't even see what's going on inside of them, but they're pretty complex. I mean, they're pretty awesome. They make the world go around and keep turning for sure. So, but it doesn't really give me it doesn't tell me what I have to bolt this on with. So, but I can't go too small of hardware and I can't go too big. And a lot of times I like to have similar hardware, but I don't have to. So on the end, we use 7/16 hardware because the bearing had a 1/2 inch hole through it. I couldn't use a half-inch bolt. I would have problems slipping the bearing over like a half-inch diameter threads. So we use 7/16, which is 0.4375. So in my mind, I'm first thinking of the symmetrical concept of design is can I just put the same hardware on the other end to hold both bearings? It would be nice if that's what I did. Sometimes when we change out bearings on equipment, we do the both ends at the same time. If we have the equipment down, we take advantage and that would be nice if I could if everything was kind of the same. Here it's I don't know if I want to make that call necessarily because that's here is they're telling me when I buy this bearing, it's going to come with this 0.6875 hole in it. 0.6875 is going to be the, or 0.687, sorry, is going to be the size of the hole in the bearing. And so if I use 7/16 hardware like I did on the discharge end, then I minus that dimension, which is I have memorized 0.4375, that's 7/16. That means that I'd be looking at this hole is potentially a quarter inch bigger in diameter. And so what that space looks all the way around is kind of divided by two. What I'm getting a look at is like how much space, how much slop is this hole on a 7/16 inch like stud or fastener? And I really got to almost, I've almost got to pretty much, if I round it up, it'd be an eighth of an inch space all the way around, which is a lot, kind of. I mean, that's a really sloppy fit of a fastener to a hole. What in worst case scenario, if you've ever built anything in your life, what you do when that happens is you put a bunch of washers on it, right? You like washer up the so that the fast, even if I put the nut on it, I'd almost have to, in this case, I'd almost have to be concerned, well, how big is the nut? Will it even like seat against this hole, or will I have to use a big old flat washer? And so to me, I feel like 7/16 hardware on this end is a little bit small. And I would be happier using a half-inch hardware here, or even up to 5/8 hardware, like a 5/8 stud. But, you know, I think different designers will make different decisions here. And this can be a good conversation piece for an engineering to say, what do we want? Do we want mismatch ends or do you want to try to make the same? And they might tell you, well, let's look for a different bearing that maybe has the same mounting size holes. And that's not in my case here. I'm like, well, I'll just make a judgment call. Let's at least put half-inch material or half-inch studs, half-inch holes, clearance holes, or I'm going to tap this for a half inch. My problem with that is it's really close to 7/16 from the other end. And so it's easy to mess up that hardware. And so I don't have a perfect scenario in mind here, but in the event when I have any decision point, I've got to make a decision, knowing that my decisions in the modeling stage can be modified pretty easy. So I can make the wrong decision at this point, kind of have this queued up in my brain to say like maybe there's some design considerations, but it's not going to prevent me from moving forward because I'm just going to make a decision and then I'm going to say, yeah, we can iron this out later. Maybe this becomes in my engineering notebook where I make a note, hey, I just got different size hardware on the ends for the bearings. Let's have a discussion at some point. And then I don't have to run off to have that discussion. I can just queue it up, knowing that my design is easy to modify anyway, and just keep moving forward. Um, yeah. So I'm gonna keep moving forward. I'm gonna just say let's make it for half-inch hardware. So what I'm gonna do is come back to this. I feel like 7/16 at least is a little too small, too sloppy. And so I need a hole here. So I'm gonna go back in. These are my points. The ends of these are where I can use for my hole command then, using these ends for where I want those holes right here, right here, right here, and right here. So I've got those 4 points through this solid, I hope. Let me X those solids out, make sure I'm going to select the right solid. It's through the same end plate solid, that one. So that hole. And then this is a threaded hole. So what we're going to end up doing is not a clear, I'm not going to use a headed bolt through here, but I'm going to use a piece of all thread that's that's got threads on it. So I want this to be threaded with no seat. I just want it to be threaded through. And the last time I did this, it looks like I used the 7/16 one. I'm just going to say this time it's half-inch. Yeah. Yep. 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 And then these are different holes. These are the holes for the bearing. I've already got the done. I've already finished the outer holes for the, yeah. Yeah, that's what yeah, they don't show up quite the same way, I guess. But yeah, these are that construction square that I drew. that has the bolt hole pattern for the bearing. It's the ends of those where these holes are gonna, it's to hold the bearing on the end plate. And they are threaded holes. Then I just need to select maybe the surface that I'm going through. This sketch actually lives on that side, so I need to say I'm going to select this surface. Then I start to see him show up. It's going to put a threaded hole in there. I'm going to say okay. I'm just going to turn off this view, and I should be able to see this the characteristics of that thread show up actually in the design. You can kind of see that that's threaded for a 1/2 inch bolt. It's on that on those sketch, and that's going to be what holds the bearing on. Um, Interesting thing about like doing parts that are laser cut is when the we're not the laser cut, this is going to be just a cut hole. The laser is going to interpret this to say, I'm going to cut it this small, and then somebody's going to have to thread this thing, like either machine thread it or by hand thread it. Like fabricators will put these things in drill presses and actually use a drill press to sometimes tap through holes. Machinists will use mills to do this. So the threading is going to be done after a laser hut like pilot hole has been cut. And lasers are pretty good at interpreting if you need a 3/8 hole in here. I know how to cut the pilot hole this size. Because when you cut these threads, you have to maintain that the thread gets cut correctly from the tap. And so when you're 3D printing stuff like this, though, you have to think differently because you have to think, I want the 3D printer to print the threads. And so that's just like jumping back and forth between 3D printing concepts and things that are going to be post, after cut, like post manufactured work that gets done. They do it differently. They'll do pilot holes and then they'll do the threading later with a specialized tool, right? So 3D printing, we can do that too. We can have our 3D printed parts, or we have to tap them out with a tap, or we can try to have the printer uh, uh, print the threads in there with us. And then we still might have to chase them with the bolt or something to clean them up a little bit in a 3D printing. But it is a different thought process to deliver the threads, and depending on your output, I guess. So that I just wanted to pause on that. But this I can turn off this sketch now. I think that was all I needed that sketch for, was to do this end plate. And now the icing on the cake is all I have to do is do a flange that matches that welds to the housing, and then this end plate is done, and my housing is really done as far as I wanted to get it before I make parts from it. So I've got one more sketch to do. I'm gonna do a separate sketch on that same face though, but it's just gonna be the parts that would accept and bolt this end plate on. So what that looks like is one more new sketch. I'm close to the finish line here. This is the new sketch face, same sketch face I used for the end plate. And then I'm just going to project that stuff over. So I've got all that done. So I've done all the work kind of. I just need to project that this flange is going to kind of look like this. I'll just project like that. This, this, back over to here. I've already got the one across the top. I need every single hole. So I'm just going to, I strategically pick like carefully which hole I want here. So I'm kind of flopping this over and coming along here and picking these holes. And then I just go into that original, like there isn't really, to me, there's no sketch for the flange. It's just matching the other sketch. And then, but there is a little bit here because what I've got to do is terminate the inside. And so I'm going to project this geometry. That's the housing, the volume of the inside. But that's not where my flange ends because I need to offset that little thickness, the skin thickness that's going to come on here, and with a little bit of tolerance, which we've been using that 30 thousandths number. I'm going to continue to use that. So I'm thinking of keeping things systematic here. And so I'm going to do an offset of this stuff here. That's all kind of construction, especially this here. This inside is not what I want part of my shape at all. It's just my reference. And what I want to do is offset that stuff now. So if I say offset, I think I can pick, oh, I think maybe it'll pick the whole thing. Yes, it's like, how far do you want to offset this? Oh, I want to offset this, the thickness of the skin, which is 12 gauge, 0.1094, just because I have it memorized from using it, but it is on our sheet metal gauge chart. And then I add my tolerance that I want to make sure that my this flange is going to fit on that housing, because that housing isn't going to be theoretically perfect. It's going to have some warpage. It's going to be a rolled part, and so it's not going to be a perfectly formed part for me. So I like to have this 0.030 or 30 thousandths added on for clearance here, and then that's where my flange really starts. And then all I have to do is extrude this thing. So if I this sketch should be good. Like I don't have everything totally constrained together. Like I think these I could like pull if I wanted to, but I think it's constrained enough for me to say finish. And these are three. This is going to be a 3/16 inch, and I'll make it a separate part as well. I don't want it to blend into this. I kind of want to see the seam between the two. So I'm going to say extrude this thing as a new part. This is my profile, which should be all one piece. Yep, it's just U-shaped one piece flange. I want it to go maybe the opposite way it's going now, like this, because it's the bolting, it's the mating surface to the end plate. And that's it. I say okay. And there it is. This is done. I'm really ready to make parts, make drawings. We'll do it right after spring break. Have a killer spring break. See you, Riley. Yeah. What's that? Yes, I will do it.